The first paradigm we're going to see in this course is called functional programming. Functional programming is important because, first of all, it's one of the simplest paradigms. Second of all, it's the foundation of all the other paradigms. That means the other paradigms are obtained by starting with functional programming and adding concepts one by one. And finally, functional programming is a form of declarative programming, and declarative programming is a very important framing concept for computer science that I'll explain in a few minutes. So our approach to functional programming is very practical. We will use it as an introduction to programming concepts, the first introduction. We will use it to introduce the concept of a kernel language. We will also use it to introduce important programming techniques such as invariant programming and recursion. And we will use it to introduce important data structures such as integers, lists, and trees. Finally, we will present higher order programming. Higher order programming is in some sense the apotheosis of functional programming. It is an enormously powerful technique, ability that is used in many paradigms built on top of functional programming. The ability to create functions, pass them as output, input, functions that return functions. So functions really as first-class entities. And this is more enormously powerful and used in many other paradigms. So for example, data abstraction and object-oriented programming is implicitly based on higher order programming. And finally, we will give a formal mathematical semantics for our first programming language for the functional paradigm. So let me now say a few words about declarative programming. In fact, declarative programming is two things. It's a long-term view and it's a short-term view. These two are actually quite different and should not be confused. So the long-term view is that declarative programming is a vision for computer science. The idea is that you just say what you want without saying how to get there. The computer figures out how to get there. So the point is, declarative versus its opposite, which is usually called imperative, is the programming by giving properties of your results instead of giving commands how to get there. So properties versus commands. So how do we make this vision real? Well, the whole history of computing is in designing of programming languages, systems, compilers, tools, etc., to make this more and more real, so that with a given amount of programming effort, we can do more. And in some sense, the whole history of computing is a progression toward more declarative, of course, and faster and cheaper, and they're all connected. The fact that we are faster and cheaper lets us become more declarative. And this is actually getting very sophisticated nowadays. For example, there is the technique called machine learning, where we have an algorithm that learns how to do something. Instead of explicitly having to tell the computer how to do something, the computer learns how to do this. So this is another form of very declarative programming. So in opposition to the long-term view, there's also a short-term view of declarative programming. This is, in fact, the use of mathematics in programming to increase the power of programming. And typically, it means the use of mathematical functions and relations, although there are also other things, but mostly functions and relations. So a computation will calculate a function or a relation, and we will use the power of mathematics to simplify programming. For example, confluency, which means that if you have a large program built out of functions that are composed together, we can evaluate in any order and get the same result. And referential transparency, which means replacing equals by equals. So this is something we know from algebra, but it's very useful also in programming. So this is very common in practice. There are functional programming languages. There are logic languages. So functional language such as Lisp, Scheme, ML, Haskell. OCaml logic languages such as SQL, constraint programming, Prolog, and so on. So the most declarative in this sense, the most powerful use of mathematics in programming is probably in SQL and in constraint programming nowadays. There are also combinations which are not usually seen as functions or logic, but they are, like XSL formatting or XSLT transforming documents using complicated conditions. This form of programming using mathematics is also called programming without state, where state is the ability to update or destructively assign data structures. So in this declarative approach, using mathematics, we don't update. We create an entity and keep it, so which causes testing, verification to be much simplified. So in this way of looking at things, declarative versus imperative is stateless versus stateful. So if you look back at the long-term view, you see declarative versus imperative is properties versus commands, whereas in the short-term view, declarative versus imperative is stateless versus stateful. So a key advantage of the functional paradigm then that we're going to see is that functions don't change. So a program that works today, it's been debugged, it works, will work tomorrow. So very little software rot. All changes that happen in the arguments, not in the functions themselves. So this is very powerful, and it is a style that should be encouraged. So there is one example where it's in fact very commonly used, the notion of a stateless server for client-server applications on the web, the notion of a cookie. A cookie is a piece of state, a piece of information that's connected to a particular client, but it's not stored at the server, it's stored on your machine at the client, and it's called a cookie. So this is an example of a stateless server. So learning the functional paradigm in this course will help us think in this style. In fact, all programs written in the functional paradigm are ipso facto, by that very fact of writing it in the functional paradigm, they will be declarative. So this is an excellent way to learn how to think in this paradigm. Now let's start programming. So we've kind of now completed the philosophical introduction of the course, and I'm kind of eager to get on to some practical programming. So we'll start programming in our first paradigm. And at the same time, of course, we're going to be learning the Oz language and the Mozart system, which we'll be using throughout the course, and in particular the editor, the interactive interface based on an editor called Emacs, which we'll be using throughout the course.